So this is an old trick. So back in the very early days of radio control, in the very early days of radio control, back in the 1960s, people were trying to figure out how to get proportional servo control and do it at a cheap consumer price point and with the kind of technology that you had available back then. And being able to have proportional control over your servo was a big deal back then. So anyway, they came up with this really simple system called Pulse Position Modulation. So if you have 8 servos that you want to control, you send out a train of 9 pulses, and the time between the pulses is 1 to 2 milliseconds long. Now that might trigger a thought in you, because if you a radio control servo has 3 wires, right? One's ground, one's power, and the third one is control. And what goes on control?
1 to 2 milliseconds.
1 to 2 millisecond long pulse. Where does that pulse come from? Well, the length of that pulse is determined by the timing between a pair of these pulses in this train of 9 pulses. So up here we have a receiver, and for the purposes of this slide, we'll just consider that RF black magic. It has an antenna on one end, and at the other end we have a wire. And what's coming out of this is this train of 9 pulses with this particular spacing. So there's a couple of interesting ICs that were available in the 60s era. Commonly called a one-shot. The proper name is a retriggerable monostable multi-vibrator.
Proper name is 8555.
What's this?
121 or 123.
Exactly. The old guys know the part numbers. Right? So interesting pins. Yeah. The interesting pins are there's a reset pin, and there's an output, which usually you can get either the high or the low polarity of that. And the way this guy works is it will be in a resting state. And in this drawing, I've shown the output resting at high, or 1. And whenever a pulse comes along, it starts a timer. And that pulse will stay low for a while. And you can determine how long a while is with a resistor capacitor programming. And anytime one of these pulses comes along, it pushes that timer out by another while. So what you can do then is you take another part. In this case, it's an 8-bit shift register, where the interesting pins are a clock input and a data input. And then it has 8 outputs, so the output of an 8-bit shift register. So if it's been a long while, that one-shot's output is going to be sitting at 1. So when a pulse comes along, it's going to, first of all, clock in that 1 into the first output position. And my screen resolution isn't quite good enough here. It's only showing 1 output. My slide actually has the second pin, so you can see a little bit better what's going on. Maybe I can get that moved around.
Scroll down.
Well, I'm going to try that.
Yeah.
There we go.
Nice.
Okay, so that first pulse comes along and it clocks that 1 into the first output position, the first servo output position, okay? And it causes that one-shot to go low for a while. And when the second pulse comes along, that's going to come along sort of 1 to 2 milliseconds later. And what will happen is, since that one-shot is sitting at a 0, it's going to clock in a 0 into that first position, but the 1 that was in the first bit is going to shift down to the second bit. So what the net result is, the output here on the pin 1 output of that shift register is going to have been high for somewhere between 1 to 2 milliseconds, depending on how far apart those first 2 pulses were. And when the next pulse comes along, right, it's going to shift the 1 down, and it will stay there for 1 to 2 milliseconds, depending on how long it is for this guy to come along. And since it was 0, you're going to be clocking into 0. So you have this 1 that's marching down with a different length. And so basically you have the 8 servos of the receiver are just connected to the outputs of the shift register here. And when you, after you send the 9th one, you wait for a long time, and the one-shot resets. So if you've got 9 of these pulses, it's going to be 16 milliseconds out here maximum. Everything's at 2 milliseconds. So you define a long time to be 3 milliseconds, and then start one of these 9 pulse frames every 20 milliseconds. So that's what was going on back in the 1960s, and basically that is still going on today in cheap radio control receivers. Now there's really modern ones that have digital receivers, digital servos, and 16 channels and so forth, and they're doing different tricks. But what this means is a couple of things. First of all, if you get, say, $5 radio control set at a garage sale, you can probably crack the receiver open, and you can probably find a couple of chips in it, one of which is a one-shot and one of which is a shift register. What's the part number for that one, Wayne? Do you remember?
I don't remember.
I don't remember it either. But anyway, you can look it up, and you'll say, well, which one of these is a shift register, which one is a one-shot, and you can find that in the part catalog, and then you can look and see which one is the clock pin, and then you just tack solder a wire onto it, right there, someplace, and run that out, and you run that into a GPIO pin of your Arduino, or your PIC, or whatever it is, your MicroPython, and you have got all 8 servo channels. And by the way, there is no such thing as a 3-bit shift register. So if you get a radio control receiver that's a 3-channel RC receiver, it's got an 8-bit shift register in there, right? They just only brought 3 of them out to servos. And besides, you're not using the shift register anyway. You're just tack soldering a wire on here. Now, actually, you can get receivers, and the one we have in Sting operation actually brings the PPM output out as a proper pin, so you don't even have to crack it open. In case anyone's interested, what is that? We have a Spectrum AR7700, which is just a generic RC receiver that brings out PPM. So just to show you how easy that is to do, I have some MicroPython code. This is not a surprise. So I've elided some of this, but this is code that would be very easy to do in any El Cheapo microcontroller. So basically all that's going on here is setting up a timer, and these magic numbers, wherever the magic numbers are, the prescaler and a period. Basically what this is doing is setting up this timer with a 1 microsecond resolution, so that I can the 1 to 2 millisecond pulse is going to come out to be a number between 1,000 and 2,000, and that's just set up, and then it's this somewhere there we are setting up timer rising interrupt. So I'm getting an interrupt whenever one of those pins come in. So on my interrupt callback handler, basically all I'm doing is, gee, has it been longer than 3 milliseconds? It's the start of a frame. And if it's not, then look to see when the last pulse came in, look to see when the current pulse came in, subtract it, throw the result in an array, and now you have all 8 of those servos as integers, and you can do math on them and scale them appropriately and so on and so forth. So anyway, that's a real cheap way to get a lot of RC channels into a simple microcontroller with only 1 I/O pin. So, and that's an old trick that people seem to have forgotten. So I just thought I would remind everyone.
I just want to walk through some actual Python code. All of this wonderful stuff. I will go very quickly. This is our plug. I'm going to put the code out on the list. A lot of this stuff, really easy to do. Download 300 megabytes of code. Configure 75 configuration files which require all sorts of information that you may not know about operating systems and Lord knows what else. And if you want to do really, really cool stuff, you eventually have to learn how to do all of that. But the first day, you just want to make your robot move. A very easy way to do that, get a refurbished bot vac. You can tell your, I can say wife, your significant other that it's to clean the house. They're like 220 bucks or something like that, I think. And you now have a robot base without all of this engineering. You get a Raspberry Pi, which, you know, for like 15 bucks, you can buy an SD card that has Raspbian on it and be up and running, and it's just like a real computer almost instantly. You connect that. Part of the reason we use bot vacs is they have a nice USB connector, and they publish all this information about how to access these parts that you bought, as opposed to almost everything else that you buy. They try and hide what it is that you got. And you are ready to make a robot move. Okay, I'm told we'll go fast. I can't show much code. But if you search for BotVac API, you'll find a document that will show you all the commands and what you can do. And this little bit of code here is all it takes to do the little motion back and forth. You know, it's a page of code. And the part that actually does most of it is overhead for messages. You know, I do get version to make sure I can talk, move forward, send a move, you know, move forward, check if we bumped, make sure the robot's still moving, and if not, give it another move command, then go backwards. That's all it takes to do a kind of interesting motion. You entertain your kids and your grandmother. I will put this out on the list. You know, if anybody wants to ask questions on the list, you know, I will be watching it every day and glad to answer. And for 300 bucks over the weekend, you can be a roboticist.
Right. Yeah. Sorry.